Hi, this is Professor Stugard, and in this video we're going to be discussing cylindrical coordinates. Now, cylindrical coordinates are really just our extension of polar coordinates into 3 dimensions. Now, typically we do this by essentially just converting x and y into polar coordinates, and then keeping z by itself. So that, again, the main idea is that our x and y, what we describe in our xy plane, we do that in terms of our polar coordinates, but we still keep z equal to z, where again, z is really, we think about in terms of our height, right? Z kind of represents our height off of that coordinate plane. And that's really all we're doing with cylindrical coordinates, is we convert to polar coordinates for our coordinate plane, and then keep our variable for height as, well, whatever it typically would be. Now, the idea is that when we use cylindrical coordinates to evaluate our triple integrals, we basically want to integrate with respect to our height first, which leaves our polar region to be the region D, which is what we do our double integral over. Now, when we make our substitution, we do need to be careful because we're substituting for dv, which again was typically equal to dz, dy, dx. But when we convert to polar coordinates, that dy and dx really become r dr d theta. And so when we kind of group and simplify, well, we have to make sure that when we substitute, we always keep track of that extra r. And again, that's a very, very common mistake when we're doing cylindrical coordinates, well, and polar coordinates as well. And then obviously the rest of the dv becomes dz, and then our dr and our d theta. So let's take a look at an example and see how we would actually use these in context. So let's say I want to evaluate this triple integral over the solid E, where E is the solid in the first octant that is beneath the surface z equals 1 minus x squared minus y squared. All right, so, well, let's sketch it first. So if I sketch this surface, that solid is going to be every single point in space that is below my surface and then also bounded by my 3 coordinate planes. That's what it means to be in the first octant. So again, we want to integrate and hit every single point inside this particular solid. And we're going to use polar coordinates. Again, I can come out, I can go up. I'm going to do polar coordinates, but then this bottom portion becomes my region D. And so my region D, which is going to be my xy plane, and notice that I labeled everything here. My region when z equals 0, well, if I plug that into my surface, remember that's going to give me my projection into the xy plane. When z equals 0, that means, again, projection into my xy plane, which is what this is. And so I get 0 equals 1 minus x squared minus y squared. But again, hopefully at this point, every time you see x squareds and y squareds, you're thinking, okay, there's got to be a circle built in there somewhere. And well, yeah, clearly if I add the x squared and the y squared to both sides, I'm going to get, well, x squared plus y squared equals 1, which is of course my unit circle, which means that my projection in the xy plane is just my unit circle, except we're bounded in the first octant, which also corresponds to our first quadrant. So my region D is going to be that shaded region in green. Now, remember, that's going to be the region I'm integrating over after I do my first iterated integral with respect to z. After I do my iterated integral with respect to z, then I'm going to be taking the double integral over this region D, which is now in my xy plane. So again, cylindrical coordinates because, well, it's the unit circle, and circles are usually much easier to evaluate in terms of my polar coordinates. So again, we keep z equaling z, and then instead of x's and y's, we're now using thetas and r's. And so theta is going to be bounded between 0 and pi over 2. Again, that's my first quadrant. And then r is bounded between 0 and 1, because again, we're hitting every single point on the interior of this circle, all the way from a radius of 0 out to that radius of 1. Well, Now I need to find those bounds for z. So I have my bounds for r and theta, but I need my bounds for z to be in terms of those r's and thetas. Now my surface z, we know it's bounded in the first octant, so we know that the lower bound of integration has got to be 0. It's the coordinate plane. So what I'm worried about now is going to be my upper bound. So this is my upper bound. My function is z equals 1 minus x squared minus y squared. Now I can just go ahead and blindly substitute my substitutions for x and for y, being r cosine theta and r sine theta. But if I can, again, hopefully see that x squared and that y squared, there's going to hopefully be a better way to do that. And in this case, if I factor out that negative sign, so that I have z equals 1 minus the quantity x squared plus y squared, well, hopefully we remember from our section on polar coordinates, or just the Pythagorean theorem, or what we know about circles to begin with, is that x squared plus y squared can be substituted for just r squared. So my upper bound for z, and then the top part of my surface, which forms that boundary, is going to be 1 minus r squared. And I'm talking about it in terms of my polar coordinates or in terms of my cylindrical coordinates. Which means z is bounded between 0, again, the coordinate plane, z equals 0, and then my upper bound, 1 minus r squared, again, making sure I'm in terms of the correct variables. All right, so here is my integral. Now that I understand my region E, and then not just understanding my region E, I understand the region D that I'm going to be integrating over second when I have my just double integral instead of a triple integral. Now I can take a look at this, and well, again, I'm going to have to substitute here, and I'm going to have to get rid of every x and every y and replace those with r's and thetas. Now, before I do, and again, I could blindly go ahead and start plugging it in, but that looks like that's going to be quite a mess. Well, what I'm going to do is see if I can factor first, because again, I see x to some powers, I see y's to some powers. Again, if I can find anywhere that I have an x squared plus y squared, that substitution is going to make my life way, way easier. And so typically, the first thing we really want to do is to factor. And again, because factoring is really, really convenient when we're doing integrals as well, especially when we're doing iterated integrals over multiple variables, because we're going to be able to factor things outside of our limits of integration. But, well, nothing is really written as a multiplication problem yet. So the first thing I want to do is factor. So look for common factors in both of these terms. The common factors are going to be, let's see, an x and a z. And if I factor an x and a z, oh, look what happens. I end up with just a x squared plus y squared. Well, now I see my x squared plus y squared. That's really convenient. So now I can just substitute everything. So again, my x becomes r cosine theta. Well, z stays z, no change there. X squared plus y squared becomes my r squared. And then the last step, and don't forget that dv, when I substitute that, is the entire expression r dz dr d theta. Again, you got to make sure you have that extra r there as well. So let's see. Now, I'm going to do kind of two steps at once now. The first thing I'm going to do is try to kind of try to simplify here because I have a bunch of r's. I have r and r squared and another r, which means I really have r to the fourth. And then I'm also going to plug in my limits of integration. So again, like I said, I have r to the fourth, cosine theta, z, then my dz, dr, d theta, and then my bounds. So and my bounds have to match up. So my first bounds are for z. Those are the interior ones, right? That's going to be the first of my iterated integrals, where I'm evaluating z from 0 to 1 minus r squared. So again, I can factor everything out that's not a z, and, well, all that really leaves me with now for my integrand is a z. And so I need to integrate from 0 to 1 minus r squared of z dz. So again, I can try to keep this all part of the same problem, but again, I have a double integral and a bunch of other things going on. I think side work is definitely the best way to go about this. So the antiderivative of z with respect to z is, of course, just going to be 1/2 z squared. I'm evaluating now from 0 to the quantity 1 minus r squared, which means you need to be really, really, really careful. Even though we're in Calculus 3, I've seen this mistake a couple of times. When we plug in our bounds, and I plug in that bound 1 minus r squared, it is that entire quantity. You must expand that with the binomial theorem, or I guess expand it by longhand. But again, if you're in Calc 3, you should know the binomial theorem, and you should be able to apply it correctly and hopefully without mistake. And of course, if we evaluate at 0, that's just 0. And so this entire thing becomes that expression 1/2. And again, I'm not distributing that 1/2 through. Again, I'm leaving everything factored because, and I can factor outside of my limits of integration. So leave everything factored. There's no real need to distribute at this point, at least not yet. And so I'm going to leave that 1/2 outside. And then, of course, when I square that quantity, I get 1 minus 2r squared plus r to the 4th. Just a reminder, hopefully you are working this out on your own paper. Pause the video as you need to make sure that you're getting the same answer as I am, or better yet, pause the video, get your own solution, then unpause the video and check your solution with me. And if you made a mistake, go back and try to figure out what it is. If not, and you got everything correct, we can just kind of move on. But now that I've done my side work, now I'm going to bring my result back and plug it back into my, well, what was my triple integral, but now is going to be just my double integral. So again, I make that substitution. Now, I know that my next bounds of integration are going to be dr, which means anything that is not an r can be factored outside. So the cosine theta, I can factor that out. The 1/2, I can factor that out. But what I am going to have is this r to the 4th. And so I'm going to have to distribute this r to the 4th through this expression before I try to take my next antiderivative. Because, well, as we can hopefully see, when I factor the 1/2 and the cosine out and distribute through my r to the 4th, well, I just get a nice neat polynomial. My polynomial now is r to the 4th minus 2r to the 6th plus r to the 8th. And we're just integrating that with respect to dr. Again, let's do this as a little bit of side work. This is a polynomial, so hopefully the antiderivative is a piece of cake. So again, do the antiderivative yourself, plug in the bounds. When you're ready, unpause the video. Because we find the antiderivative is 1/5 r to the 5th minus 2/7 r to the 7th plus 1/9 r to the 9th. And when I plug in my bounds 0 and 1, well, 1 to any power is still 1, so it's just the fractions 1/5 minus 2/7 plus 1/9. And of course, when I plug in 0, I just get 0. And as a fraction, that becomes 8 over 315. And there, the lowest common multiple for 5, 7, and 9 is going to be 315. Again, check that answer yourself. Make sure you're getting that same result, because now we're going to take that value 8 over 315 and bring it back to our problem, substitute it now, and now we just have a single integral. And again, well, let's factor out our constants. I have a constant of 1/2 now, and this constant of 8 over 315, which when I simplify them gives me 4 over 315. When I integrate, now it's just, well, cosine theta d theta, which is just sine. And when I evaluate sine at my bounds, sine of 0 is 0. Sine of pi over 2 is 1. 1 minus 0 is just 1. And so my answer for this entire triple integral becomes the value 4 over 315. So, again, a lot of work there. We have to make sure we understand the solid. We make sure we understand what our region D is going to look like after we do our first iterated integral, right? When we actually get it down to our double integral. And then it's just a lot of integration techniques, making sure we can factor and integrate properly. Let's try one more example. Let's say I want to evaluate the triple integral over the solid E of just z dv. So in this case, my integrand is fairly simple, which hopefully will be a good thing, but we need to make sure we understand what our solid is. So our solid is going to be the region bounded by x plus y plus z equals 2, and x equals 0. So those two are definitely plane surfaces. Right? There's no exponents there. They're all linear terms. So I have the plane x plus y plus z equals 2, the plane x equals 0, which that's kind of nice because that's a coordinate plane. And it's going to be inside my cylinder, y squared plus z squared equals 1. So let's take a look at what that's going to look like. Now, in this case, I used different software to actually graph what the solid is going to look like because, well, I thought this might be a little bit easier. This software is not free. You can still use GeoGebra and absolutely graph everything and try to determine where we're actually looking at here. And that's good practice, but I wanted to take a look here and we can hopefully see that, yeah, the idea is that we're inside the cylinder. Y squared plus z squared equals 1. So there's a cylinder, and we have a cylinder in space. And that cylinder in space is being chopped. We're chopping it on one side by the plane x equals 0, so just chopping it at that coordinate axis. And then we're chopping it again at an angle by that plane x plus y plus z equals 2. Now there's a few things that I'm noticing here. Like I said, x equals 0 is my yz plane. And look at my cylinder. My cylinder here, that's just in terms of y and z. Which means when I'm trying to set this triple integral up, I'm actually going to make my life way, way easier if I choose my region D to be my to be my YZ plane instead of my XY plane. So I want to choose YZ, the YZ plane, to actually be where my region D exists. And so, well, my region in that YZ plane for D, well, again, make x equal to 0. Well, that doesn't change anything because there's no x's involved here at all. In fact, I believe we looked at this same surface a while ago when we first started our multivariable calculus exploration. And y squared plus z squared equals 1, well, that's just a unit circle. That's a unit circle in my YZ plane. And again, notice I'm always, at every single step, I'm always labeling my coordinate axes. So in this case, it's y and z, and I chose it to be oriented in this direction, with z being my horizontal axis and y being my vertical. You don't necessarily have to do this as long as you're consistent throughout the entire problem, but that's how I chose to set this up. And so the way I'm going to make my substitutions now, I'm going to leave x equal to x, and I'm going to use polar coordinates in the YZ plane. This is the part that becomes my polar coordinates. Now, the way I have it set up, I'm keeping y equal to r sine theta. And that's one of the reasons that I've kept y as my vertical axis, is that if I keep y as my vertical axis, then my substitution for y is still the same exact one it was in the previous problem. Again, you don't necessarily have to do it this way, but for consistency's sake, that's how I chose to set this particular one up. And then again, we're setting up x to be our height. So now x is our height. It's not going to be z. We're basically tilting the problem so that we're thinking about it slightly differently to make our lives a bit easier. Now, for the polar coordinate aspect of this, well, it is the entire unit circle, which means theta is bounded between 0 and 2 pi. It's still the unit circle, so r is bounded between 0 and 1. And now, again, this is the key, when I substitute for dv, I still have the r in front, which is what we need, but now it's dx. Again, I'm keeping the variable x, and then my polar ones become my dr and my d theta. And if any of this is confusing, again, take some time, try to think about it, but again, the idea is that these cylindrical coordinates, the whole motivation is that, well, when I do after my first iterated integral, when I'm just, well, integrating my double integral over that region D, how did I set up that region D to make life as easy as possible? And, well, that's what we did in this particular case. But now there's still one more step before we can actually start integrating, and that is finding the bounds for x. So like I said, we have our cylinder in space, and we chopped it with our two planes. Now, the first plane, x equals 0, well, that's great. That's my YZ plane. That's my coordinate my coordinate plane for the yz, and okay, that'll be my lower bound of integration. Now, my upper bound, right? The upper bound is my other plane, the plane that slices it at an angle. Now, the issue here is that, well, I need my plane to be in terms of x. I need x equals, well, something. That means, well, all I'm going to do is try to get x by itself from this plane, which means subtracting the y and the z from both sides. So again, my lower bound is 0. My upper bound then is going to be 2 minus y minus z. Except, of course, I can't keep y and z in this problem. I need to convert both y and z into my polar coordinates r and theta. So just using the substitution from earlier, y becomes r sine theta and z becomes r cosine theta. You could, I guess, try to factor the r if you wanted at this point. I don't think it makes much of a difference. And I'm going to leave it just the way it is written. So now my triple integral over my solid E for z dv, well, I plug in my bounds. So again, we're doing theta last. So d theta last, theta is between 0 and 2 pi. Second to last is dr, or with respect to r, which is between 0 and 1. And then my first iterated integral is going to be with respect to x. Right? There's my dx, and my bounds for x were between 0 and that whole expression 2 minus r sine theta minus r cosine theta. Now, like always, let's factor everything that's not an x out. Well, in this case, when I factor everything that's not an x, that's basically everything. So all I'm left with is going to be 1 dx. This is my constant function, which means, I could do the scratch work and actually write the whole thing out. But I also know that since this is the constant function, the value of this is just going to be the difference between my bounds. It's just the length between my two bounds. So the difference there, so it's 2 minus r sine theta minus cosine theta minus 0, but well, minus 0 doesn't change anything. So I just have the quantity 2 minus r sine theta minus r cosine theta dr d theta. Again, pause as you need to. Make sure you are able to do this yourself and try these problems yourself, and then unpause the video at each step to make sure we're still doing it correctly. And now, well, what are we going to do for our next step? Well, it looks like, if I'm doing it with respect to r, there's no good way to factor just r's out, factor the thetas out, or my terms with theta. So what I'm going to have to do is actually distribute now my r squared cosine theta to each one of these terms. I need to understand that I'm multiplying this huge sum, well, I guess sort of differences. And so I definitely need to distribute. So I'm going to distribute everything first. And again, kind of do that on your own. And when you're ready, this should be what we end up with. All right, 2r squared cosine theta minus r cubed sine theta cosine theta minus r cubed cosine squared theta, and then I still have my dr d theta. And again, hopefully we're writing very neatly. Hopefully we are well organized so that these problems go smoothly and we're not making silly mistakes that have nothing to do with calculus. But I now need to integrate with respect to r, and there's really no good way to do this because it's basically sums and differences, which means I'm going to have to go term by term. I'm going to have to do this term, then I'm going to have to do this term, then I'm going to have to do this term. I'm going to have to do 3 separate antiderivative problems. Now, it's all with respect to r, so I can factor the thetas out. And so I'm going to do this as my scratch work now. So in a separate box, I'm setting up my 3 separate integrals. I'm factoring out the theta parts. So for the first one, I can factor out 2 cosine theta, which leaves me just r squared dr, which that's pretty easy. The other one, I can factor out my minus sine theta cosine theta, which just leaves me with r cubed dr, again, pretty easy. And with the last one, I can factor out the negative cosine squared, which just leaves me with, again, r cubed dr. So again, all of these antiderivatives are very straightforward because they're all just polynomials. We just have to keep track of those thetas, those cosine thetas and that sine theta that are in front. Keep track of those closely. And then just take the antiderivative. Now, these antiderivatives are again being evaluated between 0 and 1. And if you need to write it out, please write it out. Pause the video, get the correct answer, figure out what this expression is going to be. But I also know that evaluating at 0 is just going to give me a 0 for any polynomial expression. And when I evaluate at 1, well, 1 to any power is just 1. Which means that when I take the antiderivative of r squared, that first one, I'm going to get 1/3 r cubed, which is just 1/3, which combined with the thing in front gives me 2/3 cosine theta. The antiderivative of r cubed is 1/4 r to the 4th, so that just leaves me with that fraction 1/4. So minus 1/4 sine theta cosine theta, and then minus 1/4 cosine squared theta. All right, so that becomes the integrand for my last integral now with respect to theta. Now, again, I have 3 separate terms, which means I need to separate this into 3 separate integrals and 3 separate antiderivatives. Now, the first one should be fairly straightforward. What's the antiderivative of cosine with respect to, what's the antiderivative of cosine? Hopefully we know that one pretty easily, and hopefully we can evaluate at the bounds. And again, you're going to get a result for the first one. The second one, I have sine theta cosine theta d theta. Now, for me, I would use u sub and choose my u to be sine theta and finish the problem that way. I know a lot of students like to use the double angle formula as well. And so the double angle formula for sine of 2 theta is, well, hopefully you know that yourself. Otherwise, you can look it up, but you should hopefully be able to see how we can make that substitution there, and we can evaluate that part of the integral. And then for the last part, that cosine squared, there's only really one way that we can evaluate the antiderivative of cosine squared, and that is using our power reducing formula. Anytime I have just a cosine squared or a sine squared, I have to use the power reducing formula. The power reducing formula in this case is cosine squared theta equals 1/2 times the quantity 1 plus cosine of 2 theta. Again, these are all things that should just be right there sitting in your memory, in your whole bag of tricks to use when we're, again, tackling calculus 3 level problems. If not, that's kind of okay. Just make sure you have your reference sheet there so that you can kind of go through and know what you're looking at and make those substitutions and work on having those memorized. Now, when we evaluate this entire thing, well, I'm not going to tell you the exact answer, but when we go through, your final answer should just be negative pi over 4. And you're going to get a lot of things that cancel out here. You're going to get a lot of things that cancel, but I want you to do this on your own and get that practice taking these antiderivatives and using these different integration techniques involving trig functions because, well, we're going to be integrating a lot with our trig functions. All right, so that is the basics of how we use our cylindrical coordinates to evaluate triple integrals. If you have any questions, as always, please do not hesitate to ask. And as always, good luck studying.